Hello everyone. Good afternoon. I'm Himadri Gupta. I'm from School of Industrial and Systems Engineering at the University of Oklahoma. I am working as a graduate research assistant at OU Community Residence Co-Research Lab under Dr. Andres Gonzalez and Dr. Nicholson. Today, I'm going to present my research entitled as Optimum Selection of Pre-Event Short and Long-Term Mitigation Strategies for Flooding Hazard. This slide gives us a high-level overview of my presentation. First and foremost, I will give a quick overview of my study as well as my research purpose and goal. The optimization model will be provided after that, and the model will be then implemented on the Lumberton test bed with the result shown. And then finally, the conclusion will be explored as well as the future research opportunities. My study and my research is motivation comes from different sources. Especially, I want to mention some of them. In the year 2016, Zhang and Nicholson worked on the optimization model to minimize the total direct economic loss for earthquake, and then Yuan et al. Extended the model to use that for tsunami. She applied her model in for tsunami. She applied her model in Joplin test bed, and after that, Art Lurie conducted his research for multi-hazard scenario. Even in the year 2020, Omar Nofal and Dr. Van Vliet, they started working on various mitigation strategies for flooding hazard. Due to flood, any community have to face a lot of economic loss due to their building damage. Nofal and Van Vliet, they already presented numerous mitigation actions for reducing the flood loss. Then one question arises in my mind, then for which building a certain mitigation strategy is best for which will help us to minimize the total direct economic loss. This question give me the path to apply optimization technique for search for the answer. Community resilience results from the collective output of a set of elements within contributing systems. The figure provides a conceptual view of the elements that contribute to community resilience. Obvious ones are the physical element of the supporting infrastructure, the rules and regulation under which they operate, and the economic merchandise will by which they developed it, operated, and maintained. And then the optimization. The optimization can be defined as the problem-solving approach that aim to find the optimum solution to the objective function or functions, so while taking into account their other restrictions or constants. Recently, academicians have been relying heavily on this approach, and in the year 2020, Nazarian and Lim, they utilized this optimization technique to make the community more resilient, and after that, some other researchers, they also worked on multi-objective optimization framework with for making a system resilience in the sense of interdependent infrastructure network. The primary goal of this study was to develop an optimization framework for reducing a community's direct economic loss as a result of building destruction during a flood. This model will also assist the building owner in determining the optimum mitigation strategies for minimizing the building damage. This slide presents the basic elements of the objective, my optimization model. These are the sets, parameter, and decisions variable. These parameters are basically the input of my optimization model. The exact results of these models are basically the results of my decision variable. My first decision variable are the total number of buildings in the block of a certain archetype of a certain mitigation strategies. And then my second one is the total number of building, which is retrofitted from one mitigation strategist to another one of a certain archetype. So where is my main optimization model? This is mainly a single objective optimization model where the objective is to minimize the total direct economic loss. Um, and after that, the first constants of this model is ensuring that the building owner uh, are adopting all the mitigation strategies within their available budget level. The second and third constants of this model are more the balance constants for adopting this mitigation strategies. These are showing the relationship between our two distinct decisions variable. Uh, the last two constants are basically showing the nature of the decision variables, or those can be said as the non-negativity constants. This slide is presenting the method for calculating our expected economic loss after adopting a certain mitigation method of a certain buildings. This calculation method is highly dependent on the damage state of the building where the owner will go for the mitigation strategy. In this study, we are considering the 5 different damage states, like damage states 0, that is for insignificant damage or no damage at all, where damage state 4, that is a complete damage of the buildings. The figures showing the city of Lumberton and its structure are situated in relation to the state of North Carolina. The buildings in Lumberton have been color coded according to the archetypes, and Lumber River and Red Spring Creek are the two primary sources of the stream that provide water to the Lumberton east sides that are indicated here. In this space, it's presenting an overview of my case study. In the first phase, the flood risk analysis were done, which is also presented in the video. And the following that, the mitigation analysis was completed. After all this, we got the required input data for my optimization model. After that, using those data of in my optimization framework, I got the best preferred mitigation strategies for each and every flood affected buildings of Lumberton. And here is kind of an overview of my considered archetype. And here we can see that like the archetype F2 that has the highest number of buildings. And this is kind of a exposure analysis result. So where the hazard map was overlaid with the community model in a GIS environment. Then the vulnerability analysis was conducted using the developed numerically flood fertility function. And here, in this figure depicts the simulation flood hazard for the 2016 flooding event following Hurricane Matthew, which depict the condition of the flood induction and extent in relation to Lumberton. And the findings of this exposure analysis indicated that like nearby 2,857 structures are in risk of flooding. So in this case, I'm going to divide my result into three sections for analysis. We are considering long-term mitigation strategies like elevation of the first floor of the buildings. After that, we consider the short-term mitigation analysis, like using the flood barrier as my mitigation strategies. Lastly, I try to use all the strategies, all the mitigation strategies together. So now we are going to see the results of adopting only the long-term mitigation strategies. So here are the results of implementation of long-term mitigation strategies. Basically, we use two strategies. One is elevation of the building first floor for 5 feet, and another one was the elevation for 10 feet. So these two were the most expensive mitigation strategies because this will help the building owner to save their buildings for several unexpected flooding events. And then here we can see that like all the buildings are getting retrofitted from when I'm increasing my budget. But the thing is, only those buildings are getting retrofitted to the higher levels or to different mitigation strategies, which are helping the community to reduce the direct economic loss. And then I'm going to show the results of adopting only the short-term mitigation strategies. So here is the kind of my results. And if we notice that there is a certain reason, like after investing $50 million, when we are investing more, we are not retrofitting buildings because when we will retrofit, this won't help us to reduce our total direct economic loss. So nearby 832 buildings were retrofitted at a budget of $50 million. And after that, no buildings were retrofitted, even if we invest more, because it won't help us to reduce our total direct economic loss. And this is kind of a overview, like how the buildings are located in the map and then locations. And this is the same, like you will see a lot of buildings, those are not retrofitted. So, and other buildings are retrofitted. This is because those buildings will specifically help the community to reduce their overall economic loss. And this is the relationship between the investment on my budget and my economic loss after investing that amount for retrofitting our buildings. So so we can see that when we are working on the long-term strategies, when we are investing $280 million, we can just reduce our total direct economic loss even less than $20 million. Whereas when we are using short-term mitigation strategies, it won't help much to reduce the total direct economic loss. And this is because we have the highest 1.5 meter flat barrier, but in most of the region of Lumberton, they're affected by the flat depth of more than 1.5 meter. So where we have more than 1.5 meter, the use of 1.5 meter flat barrier won't help the building owner to save his or her buildings. So after that, if we go for the for all the strategies, this is kind of the result. So we are getting a combination of all the short-term and long-term mitigation strategies based on what is helping the community to reduce the loss. And this is kind of the like show how the mitigation strategies are allotted in different buildings. So it's good that all the buildings are getting retrofitted when we are investing more. So this is an overview of the invested budget versus the total direct economic loss. So it's clear that when we are investing more, we can reduce the total, we can like reduce the economic loss in a lot. And in conclusion, I want to mention that this model is formulated in a more generalized way. So this can be implemented in any community subject to the availability of the data. Additionally, in this study, I allotted each mitigation strategy for each building, but this model is flexible to use for a building as block. I mean, if a user want to consider few buildings as a single block and allotted a certain mitigation strategy, the model will still work for them. I personally believe that research is always an ongoing process to solve many and many problems. As a as a continuation of this research, I will add more objective functions to my model, which can be the maximization of building functionality or anything else. Additionally, I'm planning to add another level in my model that can be a great addition in my current model, even including the uncertainty. Apart from that, I'm also working on integrating the more machine learning algorithm to predict the mitigation strategies for buildings. Hopefully, I will come again with more advancements of my researches in next annual meeting. Thank you so much.